Okay, so last time we looked at the immediate instruction. So like add I and branch equal and load store instructions. Okay, so we will look at this add I instruction a little bit. So we need some modification. The modification is like this. So add I case. So for instance, $1, $0, and 3, which means that we are assigning the result of addition to the register 1, right? So here, this one is destination register, and this is source register, right? When we are looking at the R type, so there is operation, OP code, and first one is source register, and then RT and RD, right? And shift amount and function. This is the structure for analyzing of the instruction. I type case, this OP operation and source register. And then the third one, so this one is, can be used as a register or it can be used as destination. Okay, so this one is depending on the instruction type and remaining is immediate. So anyway, the destination in the I type should be this location, right? Just like LT. So here in the destination part here, right, register part, if this is I type, so this is I type, then we have to select LT as LD, right? So this is actually LT in the L type, and this is LD in the L type. But if it is I type, then LT, this part should be as LD, right? Destination register. So we have to insert this MUX for the immediate instruction. Okay. So let's go to the Logisim then. Okay. So here, what we have to do is, this is actually LD, I think. RS, okay, it's LD, it's okay. So this is LD. So this is actually coming from the 11 to the 15 in the L type, but for the I type, it should be from this location. Okay, so we need to add multiplexer. So we have to add MUX here. So MUX has a little bit. Okay. So instead of this one directly, let's remove this one. So for the R type, this is input of. So now this is not the 32-bit, it is 5-bit. Okay, R type case, the 0 is selected. I type case, this one. Not this one. Which is, this is T. This is chosen. Okay. And we have to give the input. Okay. So if this is 0, then R type case. If this 1, then it is I type. Okay. Okay, so then let's look at how we are executing some instruction. Before that, do you finish to implementing these mugs? So we are completing. Done. So you have to add this box. Okay. 0, and this is 1. And if 0, then 0 is coming out. If for the I-type case, then it should be 1. For the destination. Okay, so if you are completing this one, so what next part is we are making some program. So we will load some instruction in the instruction fetch. Okay, so let's go to the instruction fetch part. Okay, so there is a LOM, right? So there is LOM. So in this LOM, we will give some instruction code. Okay. So what instruction code you have to give is that first you have to learn you have to do assembly coding. So let's go. Okay. So if you are going to the simulator. Okay, so if we are going to the simulator, and what instruction we are running is, first we are running add I instruction, 1, 0, and 3. And then add I, 2, 0, 6. And then add. Okay, so we are creating these instructions. How we can look at is that we are running ensemble load, and you can see that. So this is the first instruction, 200100003. So you are adding this one into the load. Okay. Second one is here 2002006, and third one is 0021820. Okay, so you will add this instruction in the LOM. Okay, or you can go to this location 00040000 into the memory. In the memory, you can see that there are instructions. This is first instruction, and this is second instruction, and this is third instruction. Okay, and simulator is Okay. So go to the simulator and look at the instruction. Okay, so there are 3 instructions. And then what you have to do is go to the simulator. And in the simulator, you can edit, right? You can change the content. So the first one is 20010003. Second is this one, and so on. Can you edit it? Okay. So you can see that the first one is selected, right? First instruction, which is add I $1, $0, $3. So this is content 3 is add instruction, add I instruction. Okay, so let's go to the MIPS processor. Then if you are selecting the finger, then and then click it, then you can see that the value, which value is coming out. Okay. So you can see that the instruction, the output of the instruction is 200100003. That is coming out. Okay, so this is coming out. And if you are looking at the this is, I think this is source register. First one, this is source register. Source register value is 0. Okay, so 0 is coming out, and destination should be 1, right? So $1 register should be updated. So this should be 1. If this is 0, then incorrect value is coming out. So this is 0 means this instruction should be R type, but actually this is I type. So destination should be 1. Okay, this RT is actually same to the RTD in this case, and then is reading 2 or 1 value from register 0. So that register output is 0. Okay. Actually, I learned that one. Okay, so it has a 3, but anyway, if you're learning, this will be the 0, right? So that's incorrect. Okay, and this value, immediate extension, that is 3, right? Because this is a 3. So this part is a 3, and extension of the extension is a 3, and 3. And we are selecting the immediate part. I think this is incorrect. I need to initialize this one. Okay, and then anyway, for the ALU, if you are going to the ALU, then you are selecting the output, right? Using the mux. So it's depending on this function code. Okay. So if this function code in my implementation, if this is 0001, then this is selected, which is actually output of addition. Okay. So this value is depending on the design of this mux. So your decision, and that output is coming out. So what I'm doing is I'm giving 0001, which is representing addition operation. So I give the addition operation to this ALU. Then ALU is doing the addition. So this is addition result. And that is coming out. And for this mux, from the register output, ALU output, from the data memory output, I'm selecting the ALU output. And that is waiting for here. And this is load signal. If this is 1, then it is updated, register is updated. If I'm toggling the clock. Okay. So can you check all of them, and then can you run the code, run the simulator using the TIG1s. So if you're putting the TIG1s in the simulate. Just doing this one, simulate TIG1s. You can see that the clock is changing, and next instruction is coming out, which is next one. Right? It is done. Set. Okay, so there is no distance. So this is not going to be working correctly. But anyway, can you run the simulator and then check whether the output is correctly computed? So instruction is, this is I type instruction. Okay, so this is instruction part. Clear, then this is initialized to the 0. Okay. This is clear. The next one should be this one. There is a 0. Actually, this is connected to the 0. Okay. So even this is connected, temporarily disabling. Let's disable. So this is 0. Okay, so now let's see next cycle. 6. Okay, the second instruction. And Next cycle, we are adding 3 plus. Okay. So this is add instruction. So here, the source register is 1, second source is 2, and destination should be 3. So we have to change 0. So 3. Okay. So source is 1, second source 2, and destination is 3. Somebody is asking me that. Okay, so it is reading 2 register value. First one is this register is not initialized. So there is something in the register. But anyway, the output will be addition. So this is addition, and that is stored into the here. It's weird. So let me figure it out again. Let me restart it from initialize. Okay, so this is first one, 3. And this is 3. No. This is register 0. Register 0 is not initialized correctly. That's the problem. Second one. This register 0 is a 6, and this is a 6. Why register 0 is a 6? Let me, I am doing the debugging, but anyway, can you check your code is working or not? Okay. The working means that when you're learning the third instruction, which this one, what should be output is, so the output should be 6. Okay, so this should be 6. When the first one is running, this is 1. Why this is 33? Assembly code. I let out giving the assembly code. This is assembly code 200103, 20020006, 00221820. That's the assembly code. What is your question, Kim Dong-hyun? You mean this one? Mhm. You got it? So the first one, 2, 0, 0, 1, 0, 0, 0, 3. Okay, source register is 0. So this should be 0, but it's not 0. So I think it is updated. Why $0 is updated? Because I think the implementation of the register file has some problem. Destination enabled. Float value, destination. And that is updated here. It's the correct one. Destination is 1. And this is load signal 33. From morning. $0 is not initialized correctly. Okay, so it is 36. Then what's the last one? It should be 0. 33. And this should be 0. Okay. So there is some problem. So I have to give the correct value of the selection bit for each instruction. So I type case, this should be 0, right? R type case. Okay, so this is selection of immediate or register. Okay, so because of that, the code is not correctly working. Okay. And then destination is 3, 0, then destination is 2. So something is happening. So it should be 0. So anyway, this is actually you are completing this one, then this is gonna be executing those simple instruction add instructions. Okay. What is remaining instructions? Actually, we have to implement jump instruction, jump and link, and jump register, and there are many instructions. Okay. Just simply look at the jump instruction only. Okay. So how we can implement jump instruction? To implement jump instruction, what do we have to do? So for that one, what we have to do is, okay, so here there is the immediate part for the branch instruction. Okay, and for the jump instruction case, what we have to do is, among this 32-bit, we are taking out 26-bit, right? That is jump J time. So J time. Here is OP code, which is 60-bit, and remaining is address. Okay. So what we have to do is we have to extract 26-bit from this instruction. So we have to use split. And now this one, input bit width is 32-bit. So let's just copy this. So here we are taking out the 26 bit from the 32-bit instruction. Okay, so on this part, we are taking out the 26 bit. Okay. And this 26 bit will be provided to the instruction fetching. Okay, so we are giving to this component. So for this component, we are adding another input. Which is another input. So how large is it? It is 26 bit. So what we have to do for this 26 bit? Do you remember how we can make a PC value? So this should be left shift 2 bit, right? And then still we need 4 bit. The 4 bit from the current PC value. So what we are doing is we will use the splitter again. So pen out this one bit with input bit with 32 bit. Among this 32 bit, we are just taking out largest 4 bit from the PC value. To support jump instruction. Okay, so there are 4 bits. So 4 bit is coming out from the current PC value. Okay, so from the current PC plus 4 actually. So we are taking out the 4 bit from here, and then we are merging them. And there are 3 different inputs, 3 different output, and it should be 32 bit. So what we are doing is the first 2 bit, the first 2 bit is from 0. Second 26 bit is from the second one. And the highest 4 bit is from the PC value. So we are taking 0 from 1. This is front of the value. And this 4 bit from here. And this 26-bit from the constant 2-bit. Is connect to the. Okay. So this is a new jump address. So we need another mux. Whether we are selecting this value or we are selecting this value. Okay. Depending on the this is jump instruction type. Jump and this is used. Otherwise, the previous one is used. Okay. And this is address. Okay, so can you draw these jump things?
네, 안녕하세요.
Okay, I think you're following. So because I'm adding two input, address and jump, the IO will be changing. So let's go to MIPS processor. So the position will be different now. This should be 0. So I have to reconnect it. And this is offset now here. And this is jump, whether this is jump instruction or not. This is not the jump, and this is clear, and this is address. Address is coming from this 26-bit. So we are finishing the J type, J jump instruction. Okay. So are you completing everything? So now we are finishing the data pass part. So only remaining part is that here there are many inputs. Okay. So this input or this input for load, store, and selection of the logs. So the only remaining part is how we are determining these values, okay, or function part. This is not going to be needed. Okay. So now what we will do is by analyzing the instruction, we will determining these bit values. Okay. So we are completing the data pass part. Okay, data pass. So this is full data pass. So there are many mux, right? So there are mux input, and there is also another mux. And whether we are writing the signal, where this is a read or write, and there is a mux, and what's the function of the ALU. So we have to determine these control values. So that is called control pass. Okay, so after we are finishing this data pass, let's try to completing the control pass. Okay. This control pass is control value is depending on the what instruction we are actually learning. Okay, so we are designing this blue one control part. Okay, so for this control part, what we have to know is the control part. So this can be R type, or this can be I type, or this can be J type, right? So how we know that the type? We have to we know that looking at the first 6-bit OP code. So by looking at the OP code, then we know that this is R type, or this is I type, or this is J type. Okay. And so for instance, R type case, OP code value is 0. Okay. So OP code is 0, then it is R type. Okay. So 6-bit is coming. Okay, so this is OP code value. And then based on the G6 value, so everything is 0. So let us try to make a table. Okay. So let's make a table. So everything is 0. 3, 1, 2, 3. So then what's the output of each control value? Okay. So let's look at the mux. Here, the first one is this mux. Okay. So RT or RD. What this mux is called. There is nothing. So this is RT RD mux. And then second mux is, let's say here, whether this is from immediate or from the register. So this is immediate or register. And then third mux is here. Okay, so 10 mux for the whether this instruction is load store, load instruction, or this is register instruction. So that is, let's see, this is register or memory. Okay, and is there any other mux? Yes, there is a mux here. Whether this is jump or not, right? Branch or not. So it's a zero value actually. It's a branch. Let's say this is branch. And there's another control signals. Whether we are writing the register or not, write the signal, right? Sometimes we are updating the register value, or sometimes we are not updating. So like write. Any other? Memory read or memory write. So memory read or memory write. Memory read or memory write. So first one is called register destination. So instead of that, we will send this leg destination. And second one is called ALU source. Source, whether it's from the register or from the immediate value. Okay, and then some value is coming out for the ALU operation. So for the I-type case, we have to look at the OP code to know the ALU operation. So maybe we need okay. So these are signals. Okay, so OP code is 0. So then this is R-type. So R-type case, what's the destination? R-type case, the first one. What this value should be? Destination is, RD is, this is RT, and this is RD in the R-type. So this should be going out. Okay, so for R-type case, this is 1. Okay, I-type case is 0. ALU source. R-type case, which one? 0 is should be selected or 1 is selected. 0 means from the register, 1 means from the constant value for the R-type. It should be 0, right? So 0. Let's to mem. Here, mem to reg. Okay. So memory case, it is 1. Register case, it is 0. So ALU operation case, it should be 0 because memory is not going to be loaded at all for the R-type instruction. So it is 0. And R-type case, branch is not going to be branch instruction, right? R-type instruction is arithmetic operation. So branch is not going to be working. So upper part, so 0. PC plus 4. Next instruction is always fetched. Leg right, updating the register. That's true, right? Arithmetic operation case, it is updated, is 1. Memory is not read, write. ALU operation is depending on. For the function code, the last 6 bit. And then if this is not 0, then it is I type or it is J type. Right? In I type, there are 2 things. There are several things. Some arithmetic operation or load instruction or store instruction or branch equal, branch not equal. So for each part, different OP code is assigned. Okay. For the add I kind of instruction, what is register destination? Add I case. It is Alt should be used as Alt, right? So it is 0. ALU source. This is ALU source. Immediate should be chosen. So it is 1. Leg to mem. Register value or memory value. Definitely is a register value. Register value should be updated to the register. Branch is not branch. Register update, yes. Memory read, no. Memory write, no. Okay. ALU operation is add instruction. And load instruction. Register destination, ALD. Register destination is same to the RT. So it is same to the add I. ALU source. ALU source. This is first, and second one should be from the offset. So it's immediate. So it's the same to the add I case. Leg to mem. Which should be used? Memory value or ALU output or memory output for the load instruction. Memory, right? So memory read value should be used for the updating to the register value. So it is now 1. It's not branch instruction. It's not updating the it is updating register write. So it's 1. It is memory read. Memory write is not happening. And what ALU operation should be we have to do for the load instruction. It is also add instruction. Right? Load instruction case. Here, this ALU should be doing the load plus operation to compute address. Store instruction. Store instruction. Register destination. Store instruction case, actually, ALD is not going to be used. So it doesn't matter. It's a 0, 1, it doesn't matter because it's not updating the register. Actually, register write should be 0. Okay. And it's not a memory read. And it is register write, memory write. And ALU source, it is 1 because it is I type instruction. So offset should be let. Leg to mem, actually it doesn't matter because it's not using the output from the memory or ALU because it's not updating the register. Branch is not branch. ALU should be compute address. Branch equal. Branch equal case. Branch equal is updating the PC value, right? So branch equal is not updating the register. It's not reading memory. It's not writing memory. Okay. And it is branch. Register memory. Which one is used? Actually, 0 is used, right? Register is not updated, so it doesn't matter whether this is using the register value, ALU output or memory. And ALU source, branch equal case, it is computing the two register value. So it is, even though this is I type, register source should be register. And register destination, it doesn't matter because it's not updating the register value. So it is branch. And ALU output, only we will use 0 value. Right? 0. And will be used. Branch not equal is the same. J type, jump instruction case. Actually, it's not there, but there is a jump field. So everything is 0. Jump instruction case is not updating the register, memory read, memory write, and it's not branch instruction because it's always updating the PC value. Register to memory, actually register is not going to be used. It doesn't matter. ALU source, actually it doesn't matter. Destination, it doesn't matter actually. Nothing is used. And ALU operation is not used at all. Okay. So except the ALU operation, so this part, the others are just 1-bit output, right? Depending on the input value. So the input is 6-bit, so OP code is coming. Then this kind of 1 0 0 0 1 0 0 and J type is 0. This kind of output should be generated. So what component we are making is 6-bit is input and output is, first one is register destination, and then ALU source, leg to MEM. Okay, so this kind of output should be generated. So to make this kind of table, what logic do we want to use? Which one do we have to use to implement this table? So to implement the table, we have to use the easiest one is long. Okay. So address 0 0 0 0 0. The output is 1 0 0 0 1 0 0 0. Okay. So 0, 0, 0, 0, 0, 0. This is OP code. Then 1, 0, 0, 0, 1, 0, 0. This is E, 0. And area operation, let's say this is 0. Okay, 0, 0, 0, 0. And add I. What's the code of add I? Do you remember? That is 2, 0, 0, 1, 0, 0, 0. That is add I instruction. So in that case, 0, 1, 0, 0, 1, 0, 0, 0, and add like a 0, 0, 0, 1. That's the add. And load instruction, you can see that was the OP code for that. Remember, what's the OP code? The load is 8. I see. This is store. AC is what? 1, 0, 0, 0. C is, how much is it? C. 12, 1, 1. Store is 10. This is 6-bit. So load case, that address is 1, 0, 0, 0, 1, 1 case, this 0, 1, 1, 0, 1, 1, 0, 0. And OP code is 0, 0, 0, 1. Store case 1, 0, 1, 0, 1, 1 address. It has. So if the don't care X case, any value can be assigned. So let's say this is 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, is that. And branch instruction is BQ is 1, 0. So 0, 0, 0, 1, 0, 0. That's the branch. Branch case 0, 0, 0, 1, 0, 0. In the case 0, 0, 0, 1, 0, 0, 0, 0. And we give proper value for this area operation. Okay. So next time we'll continue about how to implement this control part using the loan. Okay, and we will finish this control part, and actually we can learn the program automatically. Okay, so any question? No? Okay, then see you on Wednesday. Bye. Logisim MIPS processor. Okay. You mean this top structure? Okay. Okay, see you. Bye.